So when I go through these, I'm going to assume you guys can do the Lewis structures all the way through. So I'm going to draw the Lewis structure and then provide the shape and the bond angle for the following. So we know that this is a polyatomic ion. Okay. So this molecule, I'm actually going to draw these according to the correct shape, just so that you're aware of what's 3D and what's not 3D. Okay. So this is a tetrahedral molecule, so the shape is called tetrahedral. And these bond angles are 109.5. Okay, so according to valence shell electron pair repulsion, these bond pairs, okay, are negative. So are these, so are these, so are these. They want to get as far away from each other as possible, but maintain a bonded covalent molecule. 109.5 degrees is that optimal length. This one is going to be in brackets as well, because it's a polyatomic ion. When you do the Lewis structure, it's going to look like this. This one's going to be 2D. Okay. And there is a resonance structure for this. The other option is for the bond to be over here. Good habit to draw the resonance structures. This molecule is bent, which makes this bond angle here 104.5 degrees. Okay, according to valence shell electron pair repulsion, these pair, this lone pair, and these pairs in this covalent bond all want to get as far away from each other as possible. The 104.5 degree bond angle allows the molecule to stay together, but also maximize their distance from one another. OCl2 looks like this. This molecule is bent as well. 1 or 2 lone pairs on there. It's going to stay 104.5. According to valence shell electron pair repulsion, these pairs of electrons and these pairs of electrons and these pairs of electrons all want to get far away from each other. So the bent conformation is what's best here. Now remember, when you're doing this, boron only wants 6, not 8 for its octet. This is called trigonal planar, with bond angles here of 120 degrees. According to valence shell electron pair repulsion, these want to get far away from each other. When you have 3 and no lone pairs, that optimal distance is 120. This molecule is going to go 3D. And this is called, I didn't need to circle that. This is called Trigonal Pyramidal. And this bond angle here is 105. So according to valence shell electron pair repulsion theory, these pairs of electrons, these pairs of electrons, these pairs of electrons, and these pairs of electrons all want to get away from each other. Notice in this one, you did not have the lone pair right there. The optimal bond angle for that to happen is 105 degrees. We move then on to bond length and strength. So the idea here is that the higher the bond order, the shorter and stronger the bond. And the bond order is just the number of bonds. If you have a bond order that's not a whole number, 1.3 or 1.5, that means that that bond is resonating back and forth between the 2, 1.5, or the 3, 1.3 resonance structures. Okay. So when you draw the Lewis structure for SO2, it's going to look like this, which means there is a resonance structure for it. And in this case, the bond order here, which is the number of bonds between the S and the O, well, there's 1, 1, 1, 1. We have 1 for sure. But if we do kind of a hybrid of this, we see that half the time the bond's there. And the other half of the time the bond is there. So the bond angle order here is really 1.5. And if we do SO3 2-, there is no resonance structure. So when we look at this, there's just 1, 1, 1. So the bond order here is 1. So compare the bond length and the bond strength. So the bond length of SO3 2- is greater than SO2-. Okay? So this is length. But when we look at strength, SO3 2 minus is going to be less than SO2 minus. So the reason being the bond order for SO2 is higher than the bond order for SO3. Thus, it is a shorter but a stronger bond. And the last thing we looked at is if you have bond order, now look at like we have a bond order of 2 here versus a bond order of 1, increase in bond order increases the actual quantitative value for the bond energy calculation. So they want us to determine the enthalpy, that's the delta H, for the reaction below. Okay, so I'm going to go ahead and just go through this one. CH4 plus Cl2 goes to CH3Cl plus HCl. That's balance. What I'm going to do below that now is draw quick Lewis structures plus Cl. I like to think of this as a minus sign and think of this as the broken bonds. Then I got C, H, 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 Cl plus HCl. And this as the formed bonds. It's really common for people to take this plus this minus this plus this. But you got to think of this whole side as the broken side and this whole side as the formed side. So this is going to be 4 CHs. We know that the CH energy is 414. These numbers change based on the chart you looked at, sort of, sometimes. Not that much. And this is going to be 243. So I used this, and I used that. Minus, here now, this one's nice. You have 3 CHs. So we know the CH is 414. Plus a CCl, which you know here is 331. Plus an HCl, which I know there is 431. Okay. And when you go through and do that, you should get negative 105 kilojoules per mole. That means the energy released when bonds are formed, this side, is greater than the energy it takes to break the bonds. It would look sort of like this on a chart, where this energy is this value, activation energy, and this energy here is this value, and the difference here is this value. Hope that was helpful.